Colorado.
Col how you're supposed to say it?
I say Colorado.
Colorado is correct. And we're not Coloradoans. We're Coloradans. All right, let's get started. The ratio test. Ratio test is a very nice test. When we talk about power series, let's get started. When we talk about power series, the ratio test is going to be our go-to test for power series. It often turns into students' go-to test for everything, but I would suggest a little more subtle approach to testing series for convergence, because a lot of tests work more nicely in situations where the ratio test would work. Other tests might work more nicely. All right, so our ratio test. So I'm going to say that the sum, A sub n, is an infinite series. I'm not going to put the 1 to infinity. With non-zero terms. So it could alternate, doesn't have to alternate, doesn't have to be strictly alternating. It just, the terms need to be non-zero. We're going to have three things that happen here. This series is going to converge. Absolutely. If the limit as n approaches infinity of a sub n plus 1 over a sub n is less than 1. A sub n diverges if this limit is greater than 1 or doesn't exist. Sorry, greater than 1. And 3, we have no conclusion if the limit is 0. Oh, sorry, it is 1, equals 1. 0 is less than 1, so that's good. No conclusion if it equals 1. So if we get no conclusion, that tells us you have to try something else. And the reason that this works is because this condition basically bounds our series by a convergent geometric series. This ratio being less than 1 turns into a ratio of a geometric series that is convergent, that this series is going to be bound by. So this is similar to a geometric series. Now it doesn't mean that we can find the sum of this series, it just lets us determine the convergence. So these conditions are very similar to the geometric series conditions because this ratio turns into a common ratio that we can use to make a geometric series that bounds our original series. All right, so let me, I just want to go through a couple of examples using the ratio test. I want to point out a couple of things as we go through this. Now the ratio test is nice. It's very similar to the limit comparison test because we're just finding a limit. Finding limits, we have a lot of tools for finding limits. So let's look at a couple of examples, and we'll talk about the root test, and then I want to look at a couple of other things. So the sum. And this first one is going to show an example of when we might want to use, or when the ratio test pops out as a good one to use. When we have factorials involved, the ratio test is going to tends to be a good test to use, because we don't have a way to integrate with factorials. Direct comparison can work with factorials, but factorials, when you make ratios of factorials, nice things happen. So we're testing this for the convergence. So I'm taking a look at, so we want to look at the limit as n approaches infinity of a sub n plus 1, and we're taking the absolute value, so we don't need to worry about this alternating sign. So let me back up here. Notice we have absolute values here. So we don't have to worry about this negative 1 to the n. We're taking the absolute value. So we have 2 to the n plus 1 over n plus 1 factorial, and I just immediately do the division, and I multiply by the reciprocal. And this example is nice because we can remember how to work with factorials and with powers. So we have the limit as n approaches infinity. N factorial over n plus 1 factorial. So we have an n plus 1 in the numerator, or sorry, in the denominator. And 2 to the n plus 1 over 2 to the n. 2. Because we can rewrite this as 2 to the n times 2. And there we are. As n approaches infinity, this limit is 0, less than 1, so the series converges absolutely. So the alternating series converges, the absolute value series converges, we have convergence all around. All right, let's look at another quick example. And this is an easy example with the ratio test. Sometimes this cancellation work with the ratio test takes a little bit of effort. The sum, n equals 1 to infinity, 3 to the n over n squared. So let's look at the limit. We have these powers. There might be other ways to do this, but ratio test works nicely. I have 3 to the n plus 1 over n plus 1 squared, and then I have times n squared over 3 to the n. And we get, oops, I forgot my limit. Limit as n approaches infinity of 3 to the n plus 1 over 3 to the n, I get a 3, n squared over n plus 1 squared. And as n approaches infinity, what's that limit? 3. We could multiply this out. We could do L'Hopital's rule a few times, or we could remember that for rational functions, the ratio of the leading coefficients gives us our horizontal asymptote. So we get 3, which is greater than 1, so the series diverges. All right, so a couple things I want to point out. When we use the ratio test, we're taking the absolute value of the terms, so we don't have to deal with those the alternating signs. Often students include that -1 to the n and -1 to the n plus 1 in the ratio test, and then that just complicates the calculations when you don't need to, taking the absolute value. And just be careful with how you do your cancellations when you're canceling factorials and powers. It's easy to rush through and make a mistake. And also be careful how you evaluate your limits. What happens as you go further in calculus, you start combining, your problems combine multiple techniques into one problem. You might have to take a derivative, you might have to integrate, you might have to find a limit, you might have to do some algebra. So you end up doing all these things all together. We'll see that a lot in second semester when we start talking about vector calculus, because we're doing vector operations and we're doing derivatives and we're integrating and we're doing dot products and cross products, and all these things enter into one single problem, it makes it a lot of fun. All right, questions. So, unfortunately, the root test is kind of the stepchild of convergence tests, but it's a very nice test. It tends to be forgotten, or people just don't like it. So we're going to say this a sub n is a series. Not many conditions on the root test. We have a series. It can be alternating. It can have positive, negative terms. We're not even saying it's non-zero. For the ratio test, why do we say the terms are non-zero? Yeah, we're dividing. We're dividing terms. So if the first term is 0, you could ignore it. But if you had a series that's alternating and some of the terms are 0, then you'd have a problem with the ratio test. We have 3 conditions again. Our series converges absolutely. If the limit as n approaches infinity of the nth root of the absolute value of a sub n is less than 1. Our series diverges if this limit is greater than 1. Or doesn't exist. And our third condition, if it equals 1, we have no conclusion. Sorry. 1. There we go. A sub n equals 1. So that tells us do something else. And the proof that this works is very similar to what we get with the ratio test, because these conditions are similar to a geometric series. We can do a direct comparison with the geometric series with this as our ratio. So it's a similar idea. And as you might expect, the root test works very nicely when you have powers in your terms. So let's look at a quick example of the root test. If you have powers, if you have something 2 to the n involved in your term. So if you have n powers of n, the root test is going to be very nice because those powers of n go away.
Why wouldn't you just use
Because you don't have to.
But that does the exact same thing.
Yeah. You don't have to do a ratio. You don't have to worry about your n plus 1. You just take your nth roots. Right, or if you had 0 terms in your series. So let's look at an example. So we have n squared over 2 to the n. We could use a ratio test. Well, let's use the root test because we can. The limit as n approaches infinity, we're looking at the nth root of n squared over 2 to the n. And this is just the limit as n approaches infinity of the nth root of n squared over 2. And I'm going to rewrite this. This is why this one's fun, because we get to remember some properties of roots. This is the nth root of n squared over 2. And what's the limit as n approaches infinity of the nth root of n? This is 1, and we get 1/2. The limit as n approaches infinity of the nth root of n, that was one of our common limits, is 1. Yeah. And so the series converges absolutely. I guess we're not alternating terms, so our series converges. I said absolutely, but we don't. This one doesn't alternate, so it doesn't matter. But we would get the same convergence if it were negative 1 to the n times n squared, because we have the absolute value. So we just tested 2 series in 1. All right, questions? All right, so the next thing I have is some questions for you. So let me grab a picture here. What we're looking at here, yeah, when I grab it, I'll make it bigger. So in this columns, what we want to decide is which 2 of these represent the same series. Now some of them are indexed differently, some of them have some different things going on. So we want to decide which ones are the same.
But they're indexed. -1.
No, yeah, A and C.
So this should be that should be an equals.
No, it's A and C. Oh, it's A and C.
So you can, if you're not sure, you can plug in your index and compare a few terms.
C starts at 0. No, it's A and C. It's A and C.
So the first term of this one, what is the first term of this one? 5, right? What's the first term of this one?
Not 5.
0. And the first term of this one? 5. If you weren't sure, you could compare a couple more terms. So this one was A and C. How about number 70?
What are the indexes?
This is equals, this is 4, 0, and this is 1.
B and C.
B and C?
Yeah, B and C.
Yeah, they're just shifted by 1. Shifted by 1 to the right or left, depending on which one you say is the starting with. And if you weren't sure, yeah, this one's pretty clear. You start with a 4th power, so that one's. How about 71?
What are the indexes?
This is 0, this is 1, and this is 1. B and C?
No, those are indexed the same. It wasn't shifted. It's going to be A and something.
A and B.
A and B?
Yeah.
And the first term of this one? 1, first term of this one? This is a minus here, and this is a minus. 1? So this is -1 to the 0, right? That's 1. And this is 2 minus 1, which is 1. First terms of each of those is 1. First term of this one is not 1, because we have a plus there. Okay. Yeah, that's all we needed, was not 1, right? All right. Last one.
2, 1, 0.
Yeah, 2, 1, and 0 for the indices.
C and A. No, just kidding.
I'm just kidding.
B and A. B and A.
A and B?
A and B.
I like it.
Yeah?
Yeah, A and B.
If we look at our first term here, 1/2? And the first term here?
Just keep your back, Brody.
1/2? Yeah. A and B. Because the first term here is,
Not 1/2.
B and C and C.
is it 1/2?
Yeah.
0. Yeah, this would be -1/2 because we have a n plus 1 there. Okay. So that was our title here, which are the same. One thing about the ratio and the root test. So I'm going to say a note. Ratio and root test are always inconclusive for any p-series.
That's why
So they're
it sucks.
inclusive. You probably should try this.
Right, do the p-series test.
Don't you normally go ratio test, limit comparison test, and then you direct comparison, and none of those work next?
No, I try direct comparison first, always.
P-series always take direct
This
comparison.
is the worst one, but I remember using it.
Yeah, direct comparison sucks.
Oh, that's because you think, okay, can I compare? I just think, is there a series I can compare this with?
I don't know.
So it makes you think.
How much I have to prove when I
Make
go
it
there.
difficult.
You just have to prove one term is less than the other, always.
Yeah, but
Yeah, but then
sometimes
you
you
have
like,
to, like-
yeah, but this you can't just clearly see it. So you gotta prove it in this case.
Right,
It's,
I don't know how to.
I can't just see that this is
right.
the way we do it again.
Can you go back?
Yes. So the ratio test and the root test are always inconclusive for any p-series.
Why
So-
would you not ever want to use the ratio root test slash p-series test?
Because it's a lot of work.
It's not that much. It's almost every time.
All right, some general rules.
No.
So this is just for series. Just the kind of some of the things that I think about when I do this. I would say always look at the nth term.
This is for all series. This is important.
So that means does not approach 0. Always, just that's an easy one to check. Look at your terms and see if you can tell quickly if the nth term doesn't approach 0. So that implies diverge. So look at the nth term. If you can see something about the magnitude of the nth term, that might tell you that right away that the series diverges, and then you're done. If your nth term doesn't approach 0, then you don't have to do anything else. Then look for, I would say, my suggestion is to look for special types. So that means, is it geometric? Is it a p-series? Maybe telescoping. Especially if it says find the sum. Alternating. So the geometric and the P series are especially nice when you recognize that you have that, because the rules for those are very easy. Then I would start going into your other tests. So I'd say ratio, root, maybe the integral test. Don't be afraid of the integral test. But make sure you satisfy the conditions for the integral test if you decide to use that. So just don't jump in and start integrating. Make sure that your series satisfies the conditions. And I put it at the end. I put it at the end, but I would say comparison to a special type. So this is going to be your direct comparison or your limit comparison. And these kind of fuzzy between these. On my list, I put both of these as number 3, because the boundary between these two is kind of fuzzy. And I always, honestly, when I look at a series, I think, can I do a direct comparison? Is there something that I know that I can compare this to right away? Yeah.
Are you gonna have problems on the quiz or test where it's like use this specific test?
Yes.
Okay.
So
we don't always get to choose.
right. There will be some where I want you to show me you know how to use a specific test. There will be others that you not only do you get to choose, but you have to decide what's going to work best. And there might be 3 or 4 choices that might work. 1 or 2 of them might be easier than the others. Yeah.
So it's only the integral test that we have to have the certain conditions that they
Positive and decreasing. The alternating series, you have to, if you're going to use that test, you have to make sure it's strictly alternating, so you need that -1 to the n. But that's the integral test is the one that has it has to be decreasing in order for it to work. Sean, did you have a question?
Yeah, so ratio test isn't going to be on the quiz.
I do not believe so, but let me double check.
Can we use the ratio test on the quiz? Probably a better question.
I think the quiz asks you to use specific tests. To use this test, use this test. So you show. There might be a direct comparison.
Is it like we can also use the comparison for that?
I can double check, but I think I do ask you to use a direct comparison at one point. Yeah, David. One more time? Yes, always. Yeah.
Can we use the party limit comparison test for like the approaches infinity or just
Special conditions for the limit comparison test.
Yes, but you have to use them correctly. I was telling Miss Hine, I was thinking I was going to make you, before you did that, make you show me a proof of it, but I decided that would be a little mean. Because I showed you proof of why the part that I like to use works.
But we know that the other
We know that works.
Well, Miss Hine told you. She could have lied.
But I trust her.
Be careful. Be careful. There is a table. A helpful table on page 632 that lists your tests and the conditions that they have to satisfy and all of those kinds of things. So you might want to look that over. It's a nice table. Okay. Yeah, you got to be careful. Miss Hine, she knows a lot of math, but she did study engineering. So.
That just means you can use math at some point.
No, that's not what that means.
That just means we're you a physics
I have an undergrad in physics. So yeah, do you know how does, let me think about it really quickly. How does it go?
a joke.
You know what the difference between a physicist and a mathematician is?
What?
A mathematician will say the series diverges, and the physicist will approximate it by the first 5 terms.
Funny.
The engineer might approximate it by the first 2 terms.
They thought about air resistance.
The table they looked up in their books said something about air resistance, so they decided to use it.
Without them, you wouldn't be able to have anything. Without them.
All right, there you go.